Okay, I think we can get started now. We still have people coming in, but I wanted to welcome everybody to the Science History Institute's JPS lecture on water, anytime, anywhere. We're very excited for to have our panelists here today. And please remember to type your questions into chat. And at the end of the lectures, we will get to your questions. And I'd like to introduce Daryl Boudreaux. He's a member of the JPS Executive Committee, and we're thrilled to have him hosting today. And Daryl is with Boudreaux and Associates, and I'll ask him to welcome our panelists.
Let's see, thank you. There I am. Okay, good afternoon and welcome to the September 2022 meeting of the Joseph Priestley Society of the Science History Institute. As Risa said, my name is Daryl Boudreaux and I'll be the host for the program today. The program is entitled Water from Air, Anytime, Anywhere. And it is presented by two collaborators on this work. The first is Professor Omar Yaghi, the James and E. Tretter Chair and Professor of Chemistry at the University of California at Berkeley, and by David R. Moore, the carbon capture technology leader at General Electric. The water capture technology that they will discuss is based on a very ingenious invention by Professor Yaghi called metal organic framework. I'm sure you'll hear that word during that talk. Before I turn the program over to the speakers, let me remind you to put your questions in the chat box, and we will attempt to answer all of them together at the end, rather than Omar will speak first, and then Dave will speak second, and then we'll come to the questions at the end, and we'll try to get to as many of them as we can. So if we can get started, can we switch to Omar?
Thank you, Daryl. I hope all of you can see my slides. So I would like to thank Daryl and my collaborator, Dr. David Moore from GE, for being here, and thank all of you for attending this seminar. I want to talk about a new class of materials, as Daryl mentioned, metal organic frameworks, or MOFs, and how we have been using them in general to address climate change issues, but in particular, I will focus on water harvesting from desert air. In fact, water harvesting from air, it turns out, any time of the year, anywhere in the world. So many of you may have already heard about the drying of the West. This is illustrated in Lake Mead, which is on the Arizona-Nevada border, and it supplies millions and millions of people in Arizona, Nevada, and New Mexico with water. And you see here very clearly a decline from the year 2000 to 221 to 222 of the level of water is dangerously low. It turns out that this is not just a characteristic of the West, but also in many parts of the world. The Rhine River in Europe, the Yangtze River in China, they are all experiencing low levels at this time due to the climate change problems. I think one of the things that I like to show is that the climate change problem has become increasingly personal. It affects our lives, our family, our children, because, for example, it's illustrated in how weather events have been more severe. You look here at this bar diagram, the red indicates the level of severity for those events. So in land heat waves, what was studied here is 153 events, and it turns out that over 90% of these events have been more severe in recent times. Same thing goes for ocean heat waves and wildfires and storms, drought, rain and flooding, cold, snow, and ice. All these events have been experiencing more, let's say, severity, and majority of them, or the majority of the events. And so this is being felt by the individual, and it has become a global problem. And it's not just weather, but let's say when the weather is dry, diseases are transmitted more easily by insects. Air quality. Today, if you looked in the New York Times, you see a story about the air quality degradation from the year 2008 until now. And you see across the US, because of all the fires, that the air has become more and more polluted. It affects our food supply, obviously water. So as a chemist, I would say that the periodic table is the savior of humanity. And for the last 100 years, we've been linking atoms to make molecules that have led to great materials like polymers that have transformed society and advanced our living standards, as well as pharmaceuticals. I think this century is a century of building materials by linking molecules together. And this is what I have been concerned about in my lab. So for the last 30 years, I have been preaching that linking molecules by strong bonds will be very useful in addressing much of societal problems. And climate change is that wolf coming right now to harm society. And you see in my presentation the power of the chemical bond, that when you link molecules by strong bonds, you can make robust materials that can harvest, let's say, carbon dioxide from air to address, let's say, the global warming temperatures, and as we will discuss today, water harvesting from air. The reason that strong bonds are important is because you want that material to be in a device year after year after year without having to replace it. And so that it is not just economical, but also environmentally friendly. So the chemistry I'm talking about, we call it reticular chemistry. And it's defined as the chemistry of linking molecular building blocks by strong bonds to make crystalline extended structures. And the chemists in the audience would appreciate that when you're linking molecules together by strong bonds, the challenge is to make crystalline materials. And we have, over the last 30 years, shown that we can overcome this challenge. And the result of this chemistry has been metal organic frameworks, covalent organic frameworks. So these are metal containing, you can see here that they have corners that are made from metal oxides, and these metal oxide corners are linked by organics to make extended structures. And in this, the covalent organic frameworks are entirely made from organic molecules linked by strong bonds. And more recently, we have shown how you can actually make materials that are not just rigid and open, but also they can be flexible. So it turns out that some of the smallest molecules we know are responsible for climate change and are part of the solution, like hydrogen, methane, carbon dioxide, and water. And what reticular chemistry in brief has done is to take matter and expose every atom in a material to make it an adsorptive site, meaning a site onto which one can store hydrogen or trap CO2, or in our case, as I will discuss today, water, harvesting water from air. In all these cases, you need to be able to compact these difficult to handle gases and molecules. And for that, we are able to take, let's say, a cube of sugar, which might have a surface area of 1 meter square per gram, and expose every atom to an incoming hydrogen molecule, CO2 molecule, water molecule, and therefore the internal surface area for the material increases to 7,000 meters square per gram. So what I'm talking about is a chemistry that has yielded ultra porous crystals, such that in every gram of material, you have a capacity of an entire football field to compact gases that are difficult to handle. And that's what makes MOFs, as we call them, very important, in that we can precisely design them in all dimensions. We can design the organic linkers, we can design their size, their length, their chemical functionality, and their connectivity. The same thing goes for the multi-metallic units that hold these organic units together. We can modify their size, their metal type. We can almost use any metal in the periodic table, and their connectivity. The pores can also be varied, their size, their geometry, and by virtue of changing the metals and changing the chemical functionality, we can design their chemistry. So we have really opened up a field where there's almost an infinite number of structures. And because we can precisely design these structures, they are leading to hundreds of applications, not just in climate change, but also in biotechnology and medicine. So my group has teamed up with GE through collaboration with Dr. Dave Moore, who will be giving the second segment of this talk. But in my group, we have been taking molecules, making materials out of them by linking them through strong bonds. And Dave and his team has been engineering these materials and incorporating them into systems. And as you will see, we're very close to bringing these systems to society. And that's really the order of the day in terms of taking molecules all the way to society. So in terms of water harvesting from air, the red areas are some of the areas that are experiencing water stress today because of lack of rain. And this picture will get even worse in the next, let's say, 20 years. The UN is projecting almost 5 billion people on our planet will be experiencing some kind of a water stress. So our idea has been, if you could create a material like a MOF that can trap water from air in these red regions, you would be able to trap water from air anywhere in the world, not just where it's most needed in these red areas, but also in areas such as the blue regions where there's plenty of water, but the water may not be clean. So that's our vision, is to harvest water from air anywhere in the world at any time of the year. And before any of you ask me the question of, are you going to dry the air? The point I want to make is to say that there's so much water in the air that if we were to serve everyone on our planet every day 50 liters a day, we would have only used less than 0.1% of the water that is in the air. So there is about 13,000 cubic kilometers of water in the air at any one time. So this is the challenge. Let me illustrate the challenge. The green area is where the world is hydrated or there's high humidity, and the brown area is where the humidity is low. So this is a psychrometric chart. I'm plotting on one side grams of water in the air per cubic meter of air, and on the other side, the temperature. So let's imagine that I'm in a city like Mediterranean city, where the temperature might be 30 degrees Celsius and the humidity, the relative humidity, 20%. Let's imagine I want to take that water out of the air there. And to do that, I must cool that air down to 4 degrees Celsius, which makes it extremely uneconomical. It's energy intensive, uneconomical. The way a MOF works is that because it's programmed to take water out of the air, now you are hydrating, let's say, creating humidity in a closed device that has the MOF in it. So the MOF takes up a lot of water, and therefore the humidity in a closed system would have increased from 20% relative humidity to 90%. And in doing so, all you need is to reduce the temperature by a few degrees to get to water, to get to 100% humidity and ultimately condensed water. So there aren't very many materials out there other than MOFs that work. There are materials such as zeolites, polymers, salts, they all take up water, but they have one problem or another that prevents them from being economical. For example, you need to have high capacity. Some of them don't have that. You need to have fast kinetics. Water has to go in and out with great ease so that you can harvest water over time, lots of water over time. You absolutely need to be able to trap water from air where of low humidity. Okay, that's where it's most needed. And as I said, if you can do that, then you could harvest water anywhere in the world at any time of the year. Well, the way we discovered water harvesting was with this MOF. We call it MOF 801. And it's shown here. You have the metal oxide units. This is zirconium oxide linked by organics, or zirconium oxide in blue, linked by these squiggly lines, the organic molecules, to make a porous structure. The pores are illustrated in pink, green, and yellow. That's where the water ultimately resides. But when we discovered this, it was amazing to note that the material takes up water, the red line, at almost 20% relative humidity. And it does so in a way like oxygen being taken up by hemoglobin in a cooperative fashion. That's why you have this sharp, let's say sharp knee in the uptake behavior. I think what was really more amazing to me is that you can take the water out of the pores under mild conditions, in this case, at 45 degrees C. So 42% by weight of the material was water. And you can take that water in and then take it out at 45 degrees C, which gave me the idea that perhaps we can use such material in the desert where, let's say at night, you take up the water from air when it's humid and cool, and during the day, you can, by exposure to sunlight, you can release the water. So that was our idea. And we just wanted to make sure that the water can go in and out easily. And this plot shows that this material can take in water and the water can be removed over, we show here about 80 cycles, okay? Now, you notice here that after the first cycle, you see that there is a loss of water capacity. So the water capacity here in this particular experiment is 25% by weight. After the first cycle, you see it goes down to around 20% by weight and then stabilizes. It turns out that this water, later I'll show a video to show what happens to this water. This water turns out to be the seed, let's say waters that bind to the hydrophilic sites inside the MOF, and then they act as seeds to bring in other water molecules, and therefore giving rise to the cooperative behavior that I mentioned before. So we wanted to illustrate that this MOF works not just in the lab, but also in the desert. So my students designed a prototype, which is very simple, a box that is installed within a larger box. In this internal box, you have, in this particular experiment, 1 kilogram of MOF, and it was exposed to desert air. This was in the Arizona desert. Water from air goes into the MOF, and then during the day, you close the larger box and exposed to sunlight, thereby heating the interior, and water comes out of the MOF and condenses on the walls of the larger box. And in so doing, you harvest water. This is what the box looked like. Nothing more sophisticated than plexiglass, one box within another. And this is the water that was harvested. We harvested about a cup of water per cycle. So 1 cup of water for the kilogram of MOF. And the amazing thing about this experiment, not only have you created drinking water in the desert at low humidity, but also that you've done so without any energy input aside from ambient sunlight. Okay, this is the first time in the history of humanity where this could be done in this way, with no energy input, and to be able to do so at very low humidity. Well, the water is pure, it's distilled water. And this student surprised me by sending me this video where he drank the water.
Cheers. Nice.
So both our lab and David's lab at GE tested the water and showed that in fact it's distilled. It's extremely clean water. It's ultra clean water. If you really want to drink this for a long time, you need to mineralize it to make it tasty. So another student was successful in, let's say, figuring out exactly where each water molecule resides in the structure. The reason this is important is that if we know where the water molecules reside, we can then go in and surgically modify those adsorptive sites to control how much water can go in and at what temperature we can remove that water and harvest it, so that we can aim more and more with our colleagues at GE at more energy efficient materials. So this is, for those who are familiar with chemistry, these are illustrations based on single crystal X-ray diffraction data. It's the most definitive way of figuring out the positions of any molecule. So this is a video that shows the one pore, and we're going to cleave that pore so that you can see where the water molecules go. They first go to the hydrophilic sites, the nitrogen molecules of the linker, and then once those sites are filled, they bind through hydrogen bonding across a hydrophobic pocket. So you have a hydrophilic, the interior of the pores is decorated by hydrophilic and hydrophobic pockets that repeat throughout the crystal. And this hydrophilic push-pull interaction with water allows you to also modulate the temperature at which water can be released. So based on that MOF, we call it MOF 303, and it's an aluminum MOF, the students can harvest 1 liter of water per kilogram of MOF per day. And you'll see from David that we have done much better now as we are teaming up with GE. So the vision, based on these results with MOF 303, you can then look at the weather conditions in any part of the world and calculate how much water is going to be harvested using our experimental results as basis. So the Atacama Desert is the driest desert in the world, and you see that at the driest time of the year in August, you can still harvest about 5 or so liters of water per kilogram of MOF. And I want you to also note that the MOF stays in the device for the lifetime of the device, which is 5 years or so. And at the end of the MOF journey, you can add strong acid to the MOF and disassemble it into its components, and then reassemble it using zero discharge processes. So in the Atacama Desert, in the driest time of the year, that's the worst case scenario, is 5 liters per kilo. But this goes up as you go to other parts of the world where there's more humidity. Let's say in the middle of the desert in Saudi Arabia, in Riyadh, you'd be harvesting close to 40 liters of water per kilogram of MOF per day. And I plotted other areas such as New York, Los Angeles, London, some of the Mediterranean region like Granada. You go up to about 50 to 60 liters of water per kilogram of MOF per day, and so on and so forth. So we are, I would say, with MOFs have been realizing that you can harvest water anywhere in the world at any time of the year. And it's Moore's at GE's responsibility to make this economical and widespread. But not only are we doing that, but my students are absolute heroes. They went to the Death Valley to demonstrate that, in fact, a device that fits in a small briefcase with no energy input aside from sunlight, that they can harvest water. This is shown here. This is in the Death Valley Furnace Creek, and you can see the water being harvested and the bubbles of water coming up through the device. So I think that we're onto something big here. I think that we are not just making distributed water mobile and off-grid, but you can personalize the water to your taste. You'll always deliver pure drinking water. And for me, what's exciting is that we hopefully at the end of when this is commercialized, that we would have achieved water independence for people everywhere in the world. So finally, I want to acknowledge my wonderful students and our partners and funding agencies, and then I want to hand it over to my colleague at GE, Dr. David Moore.
Thank you very much, Omar, for a very illuminating lecture. I'm sure everybody enjoyed it as much as I did, and I want to thank you for that. And we'll switch over to hear the practical end of it from David Moore. And just remind the audience, if you have questions, please put them in the chat box, and we will get to those at the end of the talk. So, David, turn it over to you now.
Great, thank you very much, Daryl, and Omar. Thank you for a wonderful talk. I'm getting even more excited than I possibly could just listening to your presentation. It's really my pleasure to be here today to follow on, tough act to follow, following Omar, to talk a bit about the work that we're doing at GE, along with Omar and his wonderful team at UC Berkeley, with the University of South Alabama, as well as the University of Chicago. We call our effort Air to Water, and what Air to Water stands for is additively manufactured integrated reservoir to extract water using adsorbents and thermally enhanced recovery. And if I really try to boil that down, it is a combination of materials, combination of advanced manufacturing, and a combination of thermal management. And it really is the combination of those three things that will drive this from, as Omar said, molecules to material, and then up to eventually system and the right types of energetics. So if I move on, the military problem statement is one that is extremely compelling. Freshwater acquisition, but treatment and wastewater disposal, they're all key logistical challenges. But if you think about just the acquisition of water, this is a huge burden for the armed forces. Bottled water, so right what I have in front of me right here, is typically what soldiers at forward operating bases and remote areas, that's how they get their water, particularly in arid regions of the world. Bottled water is typically moved by truck or flown in through aircraft, and actually comprises about 33% of the Department of Defense's budget. Amazingly, 10 to 12% of the casualties in Iraq and Afghanistan were through the transport of fuel and water. So not only is there a tremendous human element to this, there is also a cost element and the ability to be able to utilize this for humanitarian-based aspects as well. The Blue Book, the USAREUR Blue Book Doctrine says about 60 gallons of potable water is needed per day per soldier. Now this encompasses food and showering and washing of clothes, but it's about 5 to 8 liters or so per person in drinking water per day. When you think about the overall cost of water, this ranges, depending on where you are, from about $5 to over $50 per gallon. When you translate that into the cost per soldier per year, that's anywhere from $100,000 to $1 million per year per soldier. That's an incredible amount. It's about 4 to 5 orders of magnitude more than what comes out of our faucets at our individual homes. So there is a clear need for easily deployable, energy efficient, and on-site water production. So our program is a 4-year program that we're working on. It has technology synergies that could be used for things like direct air and post-combustion CO2 capture. Omar did a nice job talking about the breadth of molecules that could be utilized to MOFs could be utilized to capture. And we think that this platform is easily extendable to other application spaces. Here are some of the key program targets: sorbent capacity and sorbent life, and then ultimately the power requirement. And so you'll see a number of power requirements as we go through the talk here. But the main one here to really compete with the best systems in the world is around 420 watt hours per liter. Now, if you convert that into electrical energy per liter of fuel, I'm sorry, if you convert that into liters of water per liter of fuel, it's about 7 liters of water per liter of fuel. That is best in class today under the right types of conditions. And so the system that we've developed, again, couples unique materials with an additively manufactured heat exchanger that can only be made through additive manufacturing. It's founded on a system that we've developed for aerospace applications. And it uses a system that essentially has a trifurcating geometry where 3 different channels branch out, come back in, and continue to branch out. It allows for extremely high surface areas to volume and good fluid dynamics. And the combination of these 2 unique principles, we are coupling together to make what we call our air to water prototype. And we want the system to work under a variety of different key operating conditions, as Omar mentioned. All right, so here's how we navigate the air to water ship. Really at the core, everything comes back down into the process design, the modeling, and ultimately the techno-economics. All of these feed in and out in order to be able to move from a scale that is at the molecular scale all the way up to a macro scale. Omar and his team are working very closely with the University of Chicago, as well as our team at GE Research on artificial intelligence guided molecular screening. And through the combination of this, as well as the modeling capabilities, we're really advancing the state of art beyond anything that we could have imagined 2, 5, or 10 years ago. Omar and the team working very closely with my team here at GE Research. And how do you take the MOF 303 and other types of sorbents, integrate them into a coating, and develop the right type of process to get those into a structured system? From there, we go up and actually develop what we call our Team HX. So that stands for Thermally Enhanced Additively Manufactured Heat Exchanger. So that design, fabrication, and testing then leads into the full air to water system design and fabrication, which ultimately come back to the modeling, the process design, and you can iterate extremely rapidly on these types of processes. All right, so how does it work? Over here is one of our initial renderings of how we believe the system will work. And you start off with 4 different key steps. 1, adsorption, 2, desorption, 3, condensation, and then 4, the ability to recover the latent heat of condensation. This is extremely important. Being able to understand where the energy goes, where it does not go, is really important to be able to drive down the energetics of the system and increase the amount of liters of water per liters of fuel. All right, so in adsorption, we start off with the ambient air. It goes through the system and leaves you with moisture depleted air, and the water has been captured as part of the system. Desorption, you have 3 different mechanisms by which to drive that water off. 1 is heat, 2 is vacuum, or 3 is using some type of concentration gradient, like a sweep gas, or some combination of 2 of these or all of these. All right, that then drives off the water that is stored in that MOF to be able to get your water vapor. From there, you condense it. You either have to remove that heat or be able to use a pressure differential to take that water vapor and then condense that into pure drinking water. And so what we are really trying to drive is not just the understanding, but the capture of gains in energetics, like the isosteric heat of adsorption, the latent heat of condensation, while managing and trying to minimize the power that is needed, electrical power for fans, and the sensible heat that's needed in order to heat that system up. So this energy metric really requires not just heat recovery, but also optimal sorbent characteristics. All right, so this just gives a very high level summary of the achievements that we've made over the course of the last year and 9 months, and some of the key learnings that we're using to drive the system energetics. So we break this into 4 different parts, and then I'll continue to articulate each of these points to the remainder of the talk. Our sorbent material, MOF 303, is just a miracle material. And so the key question that we were asking here is, can a sorbent capture water across all of these operationally relevant conditions? And I think what Omar just showed you is yes. Yes, it absolutely can. It does this from anywhere from 15 even down to 10% relative humidity, all the way up to 100% relative humidity. As I said earlier, the coupling of synthetic chemistry plus artificial molecular screening is now enabling 50% higher adsorption capacities. And what we've been able to do over the course of the last 2 years or so is now scale up this material. And we have about 60 kilograms of this material sitting at GE right now. I've got one of the bags sitting right in front of me that you can see. All right, and we have about 120 more of these bags that are sitting across our labs in GE that we're now integrating into our devices. Okay, it's a beautiful material, really amazing, beautiful material. So then the next part is sorbent composite. How do you then take this material and get it into a structured composite material? And can that structured composite capture water under high airflow? Because you need to move a lot of air through the system to be able to get large quantities of water out. Does it retain the properties and the performance of that sorbent powder itself? And the fact is, it absolutely does. We can get access to all of the sorbent, even with the use of a binder that integrates this into a general structure. So we see this equivalent performance. We've got more than 1,000 cycles with no degradation, chemical, thermal, or mechanical degradation. This is a very robust system when you start to integrate this into these devices. Can we actually develop an engineered device? And absolutely we can, and we've done that. We can make pure distilled water the same way as Omar talked about his passive system. And frankly, you're going to have to mineralize this to get the right type of taste for long-term consumption of that water. We've made about 50 of these additively manufactured heat exchangers. We've coated about 36 of them, and they all show this very high robustness, and then converted that into a system with a process that we've now determined: adsorption, desorption, and condensation. We have wonderful models that really cover all of the length scales and can use this in order to rapidly integrate and iterate on the types of performance. Certainly have ways to go on driving that system energetics down, and that really is going to be the next 2 years working along with Omar and the team. So if we think a little bit about, you may be asking, well, what about commercial systems and what is the state of the art? There are a number of really wonderful and elegant systems that are out there, from WaterGen, Tsunami products, which use dehumidification, as well as Molecule, which uses a desiccant wheel. The problem is that many of these commercial systems, particularly dehumidifiers, are only operationally feasible within higher relative humidities, greater than 40%, if not 50% relative humidity, and in a narrow temperature regime. So you can see some of these materials like the Tsunami, as well as the WaterGen, they can get pretty good amounts of water, but it's only in this narrow region. Molecule, which is a desiccant wheel, can get water in broader relative humidities, but have a bit lower of this water per volume of fuel. So certainly some room for improvement. So how do we go about coating the sorbent onto the contactors? I showed you the MOF material. We have binder formulations. Think about it like a glue. And we've actually used Elmer's glue before. It works, not nearly as well as some of the proprietary formulations that we've developed. You convert that into a slurry and eventually coat this into a sorbent coated Team HX as I've shown here. Here's just one way that we actually do the sorbent integration process. We can modulate the thickness of the coating that goes onto these devices, and we can scale this across a number of different types of contactors. So here is one type of contactor that we've developed, and then we can actually coat this, and that fits in the palm of my hand. We've scaled that up to these much larger sizes. So you can see this here. This is, again, this trifurcating geometry, where you've got essentially 3 different faces that are fluidically independent, but thermally connected. And then we can coat this with the process that I showed you before. And so you can see right here, here is the coating material that is embedded in only one of those channels. The other channels do not have that material. And so you can pass through, you can dense the water, you can pass in hot steam in order to drive off the material from those channels. Now, the importance of that is that you don't contaminate that channel. You don't want to have diesel engine exhaust or other types of materials that are going through that. So it enables you to keep that water extremely pure and clean. I talked about the stability. Here is just an example of how we can coat these coupons, beautiful coated coupons with the MOF 303 plus our binder system. We can get systems that you can see right here. We can coat these and then test these over thousands of cycles. And we see no degradation of this material with not just the MOF 303, but also with our binder systems on the composite structures. So modeling across all length scales is extremely important, because this is what allows us to understand how the system works, and maybe more importantly, how the system does not work, so that we can optimize not just the energetics, but also the system design and process. Omar talked a lot about the molecular scale and using computational facilitated synthesis. We also have a great ability, partnering with Professor Grant Glover at the University of South Alabama in order to coat tubes and look at the adsorption as well as the desorption rates, feed those into more macro scale models, as well as computational fluid dynamic capabilities that ultimately then get up to the system scale. True mass energy balances that allow us to understand how certain types of geometries and certain type of process designs will ultimately work within practical application. All right, and then I'll end with this slide, walk you through the first prototype that we've developed and how it works. You can see up here is just an image of the prototype. In this reactor system here, we actually have that Team HX that I showed you before with the one channel that is coated with the MOF 303 composite sorbent, which is shown right here when you have one of these manifold plates that are off. Air flows in from this side, and we can tailor that air with the right type of humidity and the right type of temperature, and then flows out through this area into a room temperature condenser. And you can see that the air-cooled condenser that is showed right here. Over on this plot on the right, you can see temperature in degrees Celsius over on the y-axis, and the time shown over on the x-axis. You can see all these thermocouples here. We can actually get temperatures around 12 to 16 different parts of the entire system. So you can see that the temperature rising to drive off that water. We can get the temperature of the actual water that is being desorbed coming out. And one of the keys is really driving high dew point, because the higher dew point that we drive, the greater amount of water we can collect. And so you can see here is the water. We open up that port with a little bit of sweep gas. It drives off the water. And depending on the temperature in which we condense it, we'll get different amounts of water. There's about 400 to 500 grams of the sorbent that is embedded in these reactors. And Omar showed you one material that had about 40% uptake. So that gives you roughly 160 to 200 grams of water that's in there. And depending on how we run the system, we can get almost all of that water out. So the key is going forward is to be able to manage the sensible heat, recapture some of the heat that we see within that system, and increase the cycle efficiency to get the overall energetics of the system down. So it's been an absolute pleasure to work with Omar and his team. It's been a very fun program to be working on, and we're looking forward to the next 2 years where we really can make this practical and energy efficient and take these out into relevant environments for demonstration purposes. With that, I would like to thank the Joe Priestley Society. I'd like to thank Daryl for the invitation. I'd like to thank the entire audience for your attention, and I'd be happy to answer any questions with Omar as they come up. So thank you very much.
Well, thank you, Dave. I greatly appreciate this talk. It was very interesting and compelling. And as you suggest, going to move on to some questions. My colleague, Maria McInerney, has been monitoring the chat box. And so I'm going to turn it over to her. I probably will not have time to get to all of them. So she's going to use her discretion and pick the ones that she thinks are most interesting, and we'll go from there. So Maria, can you?
Yes, I hear you.
Okay.
I really enjoyed this talk. I had no clue one could take water out of air that is really dry. So thank you very much. So the first question is, what is the volume of 1 gram of MOF? I assume it's different, but the one you showed, the crystal structure you showed, what's the volume?
Well, a gram of MOF is probably about the diameter of a quarter, basically, and this high. So it's about an inch by let's say less than half an inch.
Okay, thank you. The other thing is, originally, Omar, you said 1 kilo makes 1 liter, but then David went to 70 liters. What's the difference? How did you scale it up?
So I think Omar is referring to the kilogram of material that that he developed using the passive system and the amount of water that was produced out of that particular system. Increasing the amount of liters of water per liter of fuel is going to be based on the number of cycles that you can use. So the more, if you do 4 cycles per hour, multiply that by 24, the amount that you get within one cycle, you just multiply those by the scaling factor, and that's the amount of liter that you would get per day.
Okay, thank
So
you.
hopefully that explained that.
Yes, I think. And what is the equipment cost? And again, I guess it depends on how big it is, what it is, where it is. But let's say the one you showed in the desert, which makes with your students, that is powered by the solar system. How much does that cost?
I think we have a system that employs 200 grams of MOF that is in a startup, basically, and the cost of the raw materials that to assemble that device, which only uses off-shelf components, plus the MOF, is less than $100.
Okay, but that's not the equipment you showed.
Well, the equipment showed that came from my lab, but I'm talking about a tabletop device that that this startup is aiming to deploy in like a coffee maker in your kitchen, an appliance. So the raw materials, at least at the production of a few of these, is less than $100.
Okay, and I think you said we have a lot of water in the air, but one question says, if this became a large-scale use, how does it affect weather patterns, plants, and animals?
Well, I think, well, hopefully we're not destroying water, we're just using it and it's released back into the atmosphere. So that's one thing to keep in mind. Weather conditions are changeable. There's plenty of water in the air. And like I said, there is each person on our planet could use 50 liters a day and still leaving more than 99% of the water in the air. I think if Los Angeles decides to use this in every inch of every house in Los Angeles, yes, you might want to study the weather patterns there and see what effect it is on the environment. But I'm always reminded with the analogy before automobiles became common, that people in New York City were calculating, how many horses are going to be on the road because, that scales with the population increase. And then they realize that in 10, 20 years, they're going to be covered with horse manure. And that's a lesson in the infinite innovation that humans are able to do in face of challenges. So I discourage extrapolations, but we have to be thoughtful about the long-term ramifications of what we're doing and certainly carry out studies to model those things.
Thank you. Are there any health effects from the MOFs?
Well, the MOFs are solid. They're not soluble. They are in David's devices, they are affixed on a surface and they don't fly off or anything like that. And so they're really like sand, but fixed in without floating around in the air. So, and then at the end, like I said, they can be recycled completely. And there are some companies that studied their effect on human health and didn't find any adverse effects. Obviously, this depends on the metal. In this case, it's aluminum. Aluminum is fairly prevalent in our day-to-day life. So, yeah.
Yeah, and Omar, if I could just add on to that, we've done a lot of water quality studies of the water that is produced within the system, and we see absolutely no trace of any of the MOF materials within the water that is produced. And a lot of that comes back to the fact that you are essentially distilling off water, and you have a solid structure that has no volatility.
So nothing leaks, that's what you're saying.
Correct.
Okay, Good. And then somebody wants to know if GE made MOF 303 at 60 kg scale or whether you did it in batches.
Well, I should clarify that GE did not do it. Omar and his team actually scaled up 20 kilograms themselves, which for an academic laboratory is absolutely fantastic. It's astounding. And I've said it to Omar before, but I'll say it in front of this whole population, just how absolutely amazing that was. And then we've also went out to two vendors who have now also scaled up that material as well, Novomof as well as Framergy, both who have been great partners within this program and others.
I should add that BASF has been scaling a lot of MOFs to multi-ton quantities. So I don't think making this MOF, when this MOF is commercialized in these devices, I think making it to hundreds of thousands of tons will not be a challenge, because that's already been illustrated on the multi-ton scale by BASF.
Okay, another question goes, looking 2 years out, do you think the military will have MOFs, and when will they become available to the public?
So the military will certainly be ready to utilize MOFs within these types of systems. MOFs being ready for public use, I think, is a little bit different. We're talking about the use of these enabling materials within devices. So to answer the question more related to the devices, I still think that it's in its infancy. But our first target application is working along with the military and deploying them there. There's going to have to be a significant decrease and kind of moving down the cost curve with economies of scale. But I can imagine these being used for humanitarian-based applications. I think it could be used for agriculture. It could be used for personal drinking water. It could be used for somebody taking out and going backpacking or camping. I think there's a lot of different potential applications that could be utilized. Obviously, you're going to have different form factors and different ways in order to get the water off and make sure that it's pure and the right type of drinking water. But I think that the possibilities here are virtually endless as to where this can be applied.
The next question actually just hooks into applications, but this person would like to know, apart from water harvesting, what other applications have you considered or are possible?
Yeah, I mean, good, Omar, please.
Sorry, no, Dave, please.
Sure. I mean, I mentioned earlier carbon capture, but carbon capture both for direct air capture, so taking carbon dioxide directly out of ambient air, as well as for post-combustion capture or point source capture. So we have our GE Vernova business, which was just renamed, formerly known as GE Power. We sell gas turbines that part of that fleet of gas turbines provide electricity for 1/3 of the world. Being able to put carbon capture devices at the back end of a gas turbine is a huge path forward and something that is of strategic importance to GE. So doing that and taking out the 4% or so CO2 that comes out the back end of a gas turbine is another potential application. So Omar, I know you were going to say something as well, so please go ahead.
I was just going to say that aside from clean air, clean water, and clean energy, there are a lot of other applications in the biomedical field. Once you know how to precisely design the chemical environment within these materials, their properties are that you could come up with are almost endless, including electronics. Electronic conductivity sensors, I sometimes say that if you can think it, you can make it. And so that leads to almost infinite number of applications.
Well said.
So this is my question. So how many patents do you have?
How many patents do we have? That's an interesting question. From a system level, I think we have about 4 that have been granted, and there's maybe another 10 or so that are in the works. So at least from a system level, I can mention that for many different applications. sure Omar can talk about it from the materials perspective and material systems that he's developed.
Well, I think the MOF field in academia has been like a runaway field. It's being practiced in over 100 countries. In the last, I would say, 8 or so years, there's been a runaway also in industry in terms of filing of patents that are based on MOFs. I would say thousands a year. So that gives you an idea of the tremendous activity in the field.
Yeah.
Yes, thank you. And now a listener would like to have the opposite question, but related to how clean is the water. What other molecules bind to the MOF?
Well, fortunately, the water binds is one of the strong binders. So if there is another molecule that is of the size of water or comparable size, let's say CO2, it would be kicked out by the water. But otherwise, let's say if you have octane, it won't even enter the pore. So you have a molecular-based filtration system that then, because of the chemical environment in the pore, it precisely plucks out water and only water. And water is the only thing that can go in and the only thing that can stay in there. So that's really the essence of why it's so pure. I don't know, Dave might want to add something.
Yeah, no, what I was going to say is just to build on what Omar said. In the CO2 capture space, actually water and carbon dioxide will both go into these materials, and actually the water tends to actually help the ability to capture CO2. But you can knock that water out. With this application, obviously we want the water for drinking water, but because of just the property differences between water and CO2, you can condense out that water, get pure water, and then the gas is pure CO2. So in that case, both of them are being adsorbed into the metal organic framework, but there's a very clear process for separating them out and utilizing both of those molecules.
Another question is, can you remove lead from water instead of changing all the lead piping?
There's been a lot of work on functionalizing MOFs to trap metals like lead and cadmium. So this is already in the open literature. You can, by virtue of matching, let's say, the chemical environment to the metal ion affinity for those chemical groups, you can very selectively remove metals from water, even organics. You can design the interior to remove organics. More recently, we've been interested in trapping ions from seawater. So, if you want more lithium, perhaps lithium in seawater or in brine could be removed using MOF. So, yeah, that's possible, and it's out there in the open literature.
Okay, the last two questions, I'm going to put them together. One reviewer or one listener knows that GE was making reverse osmosis membranes, or still is making. Are you planning to sell a water to drink gadget for personal use, for large use, for military use, for, I don't know, for any use?
Yeah, no, it's a good question. So we did have a water business. We actually sold that business to Suez maybe about 4 or 5 years ago. Actually, I think it's probably 5 years ago now that we sold that business. But I actually, in my former life here at GE, was the membrane and separation technologies leader. So I actually did a lot of reverse osmosis work with my team. The second part of the question is, do we look to commercialize this? And the answer is yes. We're in the process of figuring out what that right path is. What is the right supply chain? Who are the right folks to manufacture it? Is it internally? Is it externally? But this is a very active portfolio of programs that we have right now. We have an internal group we call our GE incubations team, and they've been just tremendous advocates for the technology development and the next steps when it comes to commercialization.
Okay, so Daryl is telling us that the time is up. Thanks a lot. I really enjoyed these 2 talks. Thank you.
Well, let me just say thank you to all of you as well, and to the participants who have joined us. A very interesting pair of lectures and some interesting questions. Maria, I thank you for being so attentive to the chat box. You did a great job of synthesizing that for us. And with that, we'll call your attention, should be on your screen, the announcement of our next meeting on October 20th, where the topic will be moving from oil to bio-derived chemicals, a success story. And we would invite you to join us. And thank you again for your attention. And we'll be signing off.
Thank you.
Thank you.
Thanks. Thanks, Dave.
Thanks, Omar.
Risa, back to you.